So welcome everyone to the second day of CHEP in-house symposium. So in the first session we have 4 talks and we are starting with Professor Ananthanarayan, who will be talking about hypergeometric function theory and Feynman integrals at the interface. So over to you.
Thank you very much. I'm pleased to be here to be talking about this set of investigations that we carried out with my former students. The only good student is a former student is what I say. Sudeepan, of course, will soon be a former student. He is also one of the authors of some of the Mathematica codes that we have written and published based on our researches. So the topic here has a couple of distinct modules. One is hypergeometric function theory and Feynman integrals, which of course one could study each on its own, but there's an intimate relationship between the two. And over the years, there has been a kind of cross-fertilization of these two things. And we have learned a lot about hypergeometric function theory by studying Feynman integrals and vice versa. But during the course of our research, we were using Mathematica quite a bit to try to evaluate Feynman integrals and also looking at Feynman at hypergeometric functions, that there are no real codes for many of the purposes. So what we did was to write codes of our own, almost all of which are now published, and that is the main thing that I'll be talking about. So I'll just introduce some of the key definitions for you and then tell you a little bit about a few of the representative packages that we have written. The 3 of them that I will speak about today, one of them is called the Feyn GKZ, and this has the Feynman integrals, and GKZ is named after 3 Russian mathematicians, Gelman, Kapranov and Zelensky. And so this is a merger of the two things, and recently a couple of others pointed out the relationship between GKZ theory and Feynman integrals, but there was no realization of the algorithms that were described in those papers. So our work is related to coding this in Mathematica. Then I'll talk about a package called Olson.wl. Now Olson's a mathematician who showed how to obtain analytic continuations of various hypergeometric functions using a technique that is named after him. It's called the method of Olson. It's very useful to find analytic continuations of hypergeometric functions of more than one variable, and this also needed to be coded because there was no such realization. And one of the functions that I'll talk about, which is a generalization of the Gauss 2f1, the Gauss hypergeometric function, of course, is in one variable. So there are generalizations to 2 variables first carried out by Appel, the end of the 19th century. And later it was extended to more than 2 variables by Lauricella. So Appel introduced 4 such functions called f1, f2, f3, and f4. And f2 is one of the most useful of these and also shows up in physics. So we have written this package where we find all the analytic continuations of this f2 and also describe how to numerically evaluate them, because many of these analytic continuations have issues with branch cuts, and therefore they'll be multiply defined. So the choice of the branch is very important, and the existing realization Mathematica actually was not reliable. So this particular package also has in the list of authors Marichev, who's very senior Russian mathematician, or Ukrainian actually, who works for Mathematica Corporation. He's an author of many of the functions in Mathematica, but he joined us in this endeavor of writing this package. So I'll start with a few definitions which you know from your coursework. Well, the most important definition or basic definition is that of the Pochhammer symbol, which is a ratio of 2 gamma functions like so, where x is a variable and n is an index given like this, and it's given by gamma of x plus n divided by gamma of x. Yeah. Now it is called WL for Wolfram language. So basically everything is now called WL, named after that. So the Pochhammer symbol for integers actually gets truncated after a little while, and it is sometimes called the rising factorial or sometimes called the falling factorial, but it's not necessary to call it that. The Pochhammer symbol of 1 written so is in this way is actually only the factorial. So the basic building block where everything starts is the Gauss 2f1, which has 3 parameters a, b and c and has only 1 variable, and it is written in this way. So it is called a 2f1 because there are 2 parameters in the numerator and 1 because there's 1 in the denominator, and it's a ratio of Pochhammer symbols of a and b like this and Pochhammer symbol of c, and of course there's also a factorial denoted like this with x to the power of n. And this is a generalization of the usual hypergeometric series that we all learn in high school, where a, b, and c are all equal to 1, and this is 1 plus x squared, so on, which was generalized by Gauss. He found this very fascinating, and that's why he introduced it and studied it. And so it looks like this. Okay, and it's easy to describe this for values of a, b, and c which are not integral. And there are some issues associated with when it becomes integral, which has to be treated with care. And very often in Feynman integral calculations, it's precisely that which shows up for integral values, so it has to be done with care. So this x in Feynman integrals often would be, let us say, the square of a momentum, or a ratio of a square of a momentum to a mass. And so that would be for instance, in a bubble diagram, there would be only one kinematic variable. But if you have others, more than one leg, then you can have ratios of masses, ratios of momenta to masses, and so on. That is why you expect to see a generalization of this to hypergeometric functions in more than one variable. And you also expect to have, parameters like this a, b, and c generalized in a suitable way. And this will contain, among other things, the dimensional regularization parameter epsilon sitting over here. Powers of the propagators, etc., will show up in the a, b, and c. And of course, the Gauss hypergeometric functions also satisfies an ordinary differential equation. This has to be an ordinary differential equation because there's only one variable, and it looks like this. And with any such ODE, it's necessary for you to discuss the singularities, what the singular points are, and in this particular case, it's 0, 1, and infinity. So this particular thing, as you can see, converges for mod x less than 1, and it's easy to find the analytic continuation of this for mod x greater than 1. You can try to do it for 1 by x, which is what we always do, and get a suitable analytic continuation. So therefore, by just looking at the slide, you'll be able to figure out for yourself what the generalizations are that are needed. The ODE would be replaced by a PDE if you have more than one variable, and instead of having singular points for two variables, you will have singular lines, and if you have three variables, you'll have singular surfaces, and so on. And these singular points, singular lines, and singular curves will separate various regions of convergence of these hypergeometric functions, all of which are necessary depending on what problem you are studying. Another very crucial thing is that the 2F1 also admits an integral representation that looks like this, and let's just spend a second looking at it. So this a, b, and c looks like this. There's a dummy variable of integration. We have chosen the region of integration to be 0 and 1 in this. And then you can see that the variable of the left-hand side shows up here. It sits along with t, and the parameters a, b, and c are going to sit up here in these exponents. So analogously, it would be nice to have integral representations of other hypergeometric functions in more than one variable, but then it wouldn't be such a straightforward thing because there would be all kinds of relations that would have to be enforced in such an integral representation. You would have to introduce more than one dummy variable of integration, call them t1, t2, t3, and then there will be relations between them because such a hypergeometric function would have to satisfy a system of PDEs and not just an ODE. And this whole GKZ theory actually rests on trying to implement that thing properly and trying to obtain the actual hypergeometric series in terms of an integral representation that you start out with. Why an integral representation? Well, we are dealing with Feynman integrals. So Feynman integrals have to be brought to a form that is an analogy of this particular thing, and then this thing would have to be treated, and then you want to extract from this a suitable hypergeometric series representation. And that is the whole subject of Feyn GKZ that we have looked at. So here are various examples of analytic continuations of the 2F1. And everything that we do actually is just based on these ideas, not just for one variable, but more than one variable. So that is the story as far as our work is concerned, is to look at 2F1 as a template of a hypergeometric function, one variable, and just keep on using it many different ways again and again by suitable generalizations, suitable extensions, and also having to deal with the additional complexity of the hypergeometric function in more than one variable. So returning now to the Appel F2, it looks like this, where you can see what it looks like over here. For instance, let's describe this 2F2. So it has the following 5 parameters, A1, B1, A, B1, B2, C1, C2, that looks like this. And it's written in this particular way, again, x to the m, y to the n. But the crucial thing is that the m and n are interlaced over here. If they were not interlaced and m and n were not talking to each other, it would just be a product of two hypergeometric functions of one variable each, not at all interesting. This is what makes it interesting, the fact that these summation indices are interlaced in this particular way. So this is what Appel introduced, and then the region of convergence. You see, in all this hypergeometric function theory, it's not necessary, it's not enough just to give the series representation. You also have to give where this thing is going to converge, otherwise it makes no sense. And if you know where it converges, the next thing you have to do is to figure out its analytic continuations. Okay, so here's an example F2. The hardest out of all of them is F4, which has this very peculiar structure. The m plus n shows up in both of them, and it has this peculiar region of convergence. Well, I can't say it's peculiar, that's how it is. That's all there is to it. Here is a simple example of a Lauricella function in 3 variables, z1, z2, z3, and it's also interlaced in this particular way with this domain of convergence. Feynman integrals, on the other hand, and you have seen this again and again during the course of this in-house, is a bunch of propagators that looks like this, that shows up in the denominator. And what is of interest to us are only scalar integrals, because as Sudeepan mentioned yesterday, all master integrals that you're interested in are scalar integrals. All kinds of tensors and vectors and so on eventually, or spinors eventually, get expressed in terms of master integrals, which are all scalar integrals. So you don't have to bother about having various factors of momenta of the loop integral of the loop variables over here, and this is the simplest way of writing such a thing. So here's an L loop integral with a bunch of propagators like this raised to various powers, and with all these integrals like so. So one loop is therefore only one loop integration. If there's 2 loops, more than one. And of course things get complicated because of the way in which the momentum is routed through these internal lines and so on. Okay. Here are the simplest examples. Tadpole looks like this, bubble looks like this, there's only one momentum. Here also there's only one momentum because of momentum conservation. Here's the sunset, which is different because it's a 2 loop integral like so, and it is harder to describe it because of the fact that the internal momenta get linked to each other. So we studied along with Shayan Ghosh and Samuel Frio, who is one of our most durable collaborators. A lot of what we have done we owe to Samuel for his expertise and also participation in these projects. So this sunset over here turns out to be something that is related to Lauricella functions, and we looked at all kinds of analytic continuations. Furthermore, these Feynman integrals satisfy differential equations which look like this, and here is on the left hand side you can see that there is a bubble diagram like this. Here is another bubble where this wavy line means that the k squared is going tending to 0 plus so on, with proper boundary conditions given like this. And here you can see why hypergeometric functions enter over here, and the boundary condition for this bubble over here involves the Gauss 2f1, and as I told you earlier, the parameters involve powers of the propagator and also the dimensional regularization parameter, and x over here is k squared by 4m squared. So you immediately see why hypergeometric functions have to enter our study. Other examples, for instance, a one loop 2-point function, B naught as it is known in the literature, the Passerino-Veltman nomenclature. B naught is something that involves the Appel F4, and it's something that looks like this, with 1 epsilon, 2 minus epsilon, x and y being this and this, and 1 squared, etc. The one loop 3-point function involves the F2, and the sunset with unequal masses involves Lauricella functions. Now let us say that you have a particular diagram that you have evaluated, and the kinematic configuration corresponds to this red point over here. But the original domain of definition is only converging in this diamond over here, and therefore having the series expansion over here is of no use. You necessarily have to find the analytic continuation into this particular region. And that's why the entire hypergeometric function theory has to come to your rescue in order to do that. So here is a list of all the packages that has come from our group over here. As Sudeepan mentioned yesterday, conic hulls was done by Sumit as part of his PhD exam. But it's also important for you, Sudeepan, to know that this particular work came from the work that was first done by Shayan, which was not published. And conic hulls actually rests on the code that was developed by Shayan, which was not published, with the guidance given by Samuel, and also because of all the coursework that all of you had to endure over here, where you actually learnt Mathematica and so on. Okay, So this find GKZ over here was done by these people. Olsen was done by 5 minutes, okay, by Shovik and Tane and Samuel and so on, okay. So here are these packages, and of course I will not be able to describe them, but my aim in this talk is to encourage students to try to download these packages and use it also for purposes of education. This algebraic relations package that we wrote actually exhibits some very nice way of reducing complicated Feynman integrals to simpler Feynman integrals, but this for the moment works only for the one loop case. And this is based on an algorithm that was given by Tarasov many years ago, but he had actually not coded it. So in the path to coding this, we found various simplifications, and this is now published in Nuclear Physics. And then it has its own README file, and it has example notebooks and so on, which you could use and study how to get, a hang of Feynman integrals that prima facie look rather difficult, but actually can be simplified to look at far more interesting and useful things. The precursor to all this work was this code that we invented with Ratan Sarkar, former student, who Sudeepan has also worked with and mentioned, and Abhishek Pal, who was an undergraduate student here, and Sunetra Ramanan, who is in IIT Madras. So here is an example of how to deal with a two-loop Feynman integral which has more than one mass scale. For instance, in pion-kaon scattering, there are two mass scales, mass of the pion, mass of the kaon, and the kaon is much heavier than that of the pion. So it would be nice to have an expansion in ratios of masses of the pion to mass of the kaon, and to have a systematic expansion in this. Now, it's not like doing a Taylor series in this mass, because these are all sitting inside the integral representation. So in order to get a series that makes sense in such ratios, you have to introduce other techniques, and this is based on something called the method of regions, first introduced by Smirnov and Beneke, and they also had a code which did it, but we found a systematic way of doing this using the Landau equation analysis, and it's now become fairly popular and is being used by many of the practitioners in this particular field. So here are a few words about this GKZ package. So the idea is to take Feynman integrals and turn them into GKZ system by rewriting them in a certain integral representation which is known as the Lie-Pomeransky representation. All of you have heard of Feynman integral, Feynman representation, Schwinger representation, but it's surprising that only about 20 years ago there was another useful representation found by Lie and Pomeransky, which actually allows us to build a bridge and take a given Feynman integral and express it in terms of an integral that looks very much like the Euler representation of the 2f1, in this case for hypergeometric functions of more than one variable, because it is supposed to be expressed in terms of PDEs described by these people, Gelfand, Kapranov, and Zelewinski. So once it is turned into this GKZ system, then you have to get the hypergeometric series, which is far more complicated than doing it for the 2f1 case. So there's a method that is known as triangulation, which after you get the Lie-Pomeransky representation, it can be used and coded algorithmically to produce the hypergeometric series. And the triangulation part of it was done by Sudeepan as part of his PhD thesis. There's an alternative method to that, which is an extension of the method of Frobenius for ODEs. There's a corresponding system that is known as the Grobner deformation method for PDEs, and this part of it was coded by Shovik as part of his PhD work. So this code also has become quite popular and is being at least studied by experts, and it has picked up a fair number of citations, but I'm not sure that people are actually downloading it and using it. So the way forward is for our own community to do it. So here is an example of a bubble diagram and how to rewrite it in terms of an Euler representation that looks like this, and to eventually get the answer, which in this case turns out to be a bunch of various hypergeometric functions of two variables, part of the Appel series, which was further generalized by Jacob Horn, and these are known as the Horn functions, etc. And this is the kind of answer that you get. Similarly, in this package Olsen, we have found a way of obtaining various analytic continuations using the method of Olsen, and also in the two-dimensional case to be able to determine the regions of convergence completely. That's why it is called ROC2. This is also named after Jacob Horn. Horn actually extended the Cauchy ratio test and the Gauss test and so on to two variables. Beyond two variables, actually, the theory is not even known. It's known in principle, but in practice, it is very difficult. So please don't think that mathematics of the 19th century is all solved and there's nothing to do. Of course, you don't do it just to amuse yourself. You do it provided there is a reason to do it and there is some motivation for doing this. And I'm sure in the years to come, we'll have to go back to many of these topics because it's very important to have analytic solutions to Feynman integrals. So this is what is done in this particular package that is called Olson. And it's a very simple, user-friendly package that I would recommend for your use. So this is a way in which you start out with the diamond where the series converges and then you obtain the other regions using various transformations. PET stands for Pfaff-Euler transformation. There are different kinds of transformations. The package actually can call any one of these transformations in order, and the user has a lot of flexibility to use what he or she wants to do. And finally, here is this appel F2 also, which numerically had a problem, and now we have solved it completely for the case when x and y are real. So there are other the directions which can be explored by students, merging dispersion relations and Feynman integrals. There are many mathematical properties of Feynman integrals associated with Hodge structures and so on. There's a book by Stefan Weinzierl, which is 900 pages long. It's a superset of everything that mankind knows about Feynman integrals, especially analytical methods, but many of them have not been completed. So those of you who are interested in weekends, when there are no cricket matches and you want to do something with your life, I would suggest that you look at Weinzierl's book and look at many of the unsolved problems there and try to use them and solve them using our packages. So I think I'll stop here. Thank you.
So thank you, Professor Ananthanarayan, for your wonderful talk. So we can take maybe one or two quick questions. Yes.
Yeah.
Decomposition.
Yes.
That's different from what comes from loop tools or one of these things? Or?
Yes, yes. See, these Feynman integrals, when they are sufficiently complicated, there are many, many things which have not been explored. So the Tarasov had this.
Meaning many legs at one loop, or how many legs?
Any number of legs. So again, the complexity increases exponentially. So this particular package that we wrote allows you to make some manipulations. On the left-hand side, you may have, let us say, an integral with two mass scales. On the right-hand side, it breaks up into a sum of many different integrals involving only one mass scale. And if you know that if there's only one mass scale, you often know the answer analytically. So an object that you started out with whose analytical answer is not known, on the right-hand side, you get objects, sum of, but of course the complexity is pushed into the fact that you have more than one Feynman integral, but each of them is simpler. These are all actually things just being scratched on the surface. Now, one loop, of course, is only one loop, but still even that shows so many interesting features. And the other key thing about that is that on the left-hand side, you have an answer of hypergeometric functions of two variables. On the right-hand side, you have hypergeometric functions of only one variable each. And so these give what are called connection formulas between hypergeometric functions, many of which are actually not known. In principle, all of them are known, but they are not necessarily tabulated, let's say, in the DLMF or in Abramowitz and Stable.
Are there more questions?
Yeah, there's one.
Thanks, very very nice. So these families of integrals, I mean, you have the iterated integrals, the Goncharov polylogs that have this whole structure of algebras and also concepts of transcendentality. I never heard anything like that for hypergeometric type things. Do you know if there's any even an inkling or a no-go theorem there that you cannot, besides the relations that you indicated, is there any kind of algebra structure there?
There is. At one loop, as you know, every one loop integral is at most a multiple polylogarithm. At two loops, you start seeing elliptic polylogarithms. At three loops, you see Calabi-Yau structures and so on. So these are all known things. But when these are expressed in terms of hypergeometric function, also there are relations where one can go back to various books on hypergeometric functions and see whether there are relations. And I'm sure that they are. The thing is, not enough attention has been paid to the hypergeometric part of the theory. It's become much more, Hopf algebras and all these things. But as far as I can see, our group also has 1 or 2 papers in that direction. They have not particularly helped in actual evaluation of real life integrals. So, and in fact, a year ago or a year and a half ago, I asked Stefan Weinzierl about some of these approaches that he has himself advocated. But he said at the end of it, I want to do this numerically, compute these iterated Chen integrals. So there are all these things. Probably there is a bottleneck or a roadblock in terms of implementation. And at this point, numerical evaluation is simpler. But who knows? Tomorrow there may be some other mathematical tool which will help us simplify this and put this on the computer. Yes.
They're all known. Okay.
At least at certain loop orders. Shridipan would know better, but definitely at the level of 2 loops and so on, we do know what these A systems are and what kind of PDEs are. Actually, the first paper was written by Regé in the 1950s, where he actually saw the connection between these. Again, many of these things are known in principle, but in practice, it is not clear how difficult these things are. So I gave this talk at Bonn, and Albrecht Klemm was a well-known string type person. So he was not happy with our FNGKZ because he said that this only solves what is known as the degenerates case, which we also know. We know that it's only the degenerate case. You should do this with a non-degenerate case because it shows up in string theory and so on. That is one direction in which these things can be extended also.
Thanks. So we thank Professor Ananthanarayan again. So now